Good morning, teenagers. This is Mr. Williams. It's good to have you in class today. I'm sorry that I cannot be here. I am at the district office today. So this video is for AP Physics 1, and we are going to be exploring kinematics a little further today. Today is October the 1st, 2019. And yesterday in class, I explored with you the derivation of an equation from your graphs. I'll just briefly remind you about it. These are the notes that I gave yesterday. We looked at a velocity versus time graph yesterday that looked like this. And we asked ourselves if a car continued to move at this initial velocity, how far would it go? And the answer was it would go this distance in the blue box. But then the car actually accelerates. So how do we find the actual distance it goes? And the additional distance it goes because it speeds up is x is equal to 1/2 at squared. But the distance that it would have traveled if it had continued moving at its initial speed is v initial times time. So when you put that all together, you get that the change in distance is equal to v initial times time plus 1/2 at squared. We spent pretty much all day yesterday going over this, and one of the more difficult parts about this was to recognize that the length of this side of the triangle is acceleration times time, and the base of this, the bottom of this triangle down here, is time. So to find the area, it's going to be 1/2 of this rectangle, and the rectangle, the area inside the rectangle is acceleration times time multiplied by time. So 1/2 of acceleration times time squared. That was one of the more challenging things yesterday. And to help you with that, we had looked at the acceleration versus time graph for the same motion and noticed that that if you found the area underneath here, you were finding the change in velocity, and that change in velocity is your time multiplied by your acceleration. And that gives you this length here. Because this one was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 meters per second. And lo and behold, your velocity in this graph had increased from 1, 2, 3, from 3 up to 15 meters per second. And 15 minus 3 is 12 meters per second. So it turns out that the area under the acceleration versus time curve gave you the change in your velocity, and that change in velocity was equal to acceleration times time. That's just a brief review about what we did yesterday. Today, I am going to be rederiving that exact equation, but instead of using graphs, I am going to be using algebra. Because you can come up with these kinematic equations multiple different ways. So the topic today is kinematic equations. This word kinematic, K-I-N-E, it's a root that, so kinematic means the study of motion. So I think that's all I need to say about that. Kinematic is the study of motion. So kinematic equations are equations regarding motion. I'm going to start our little exploration today with a definition. acceleration is defined as A is equal to the change in V over the change in T. We've gone over this before, so this is not new. What if I solved for VF, my final velocity? I will remind you that delta means the change in, and mathematically the change in means the final state minus the initial state. So that means acceleration is the final velocity minus the initial velocity over the final time minus the initial time. But I'm solving for VF, so there's no real reason for me to get into the weeds with delta t. So I'm just going to leave it as delta t. Using my mad algebra skills, I'll multiply both sides by delta t. And then I'll get A delta t over here is equal to VF minus VI. I'll add VI on both sides. And when I do that, I'll have VF by itself. But in mathematics, we usually like having the thing that's all by itself or that's solved for on the left-hand side. So I'll write VF is, I'm doing it in my head now, but you're AP kids, you should be able to keep up. VF is going to be equal to VI plus A delta t. What I did in my head was I added the VI on both sides. Oh, good God, I screwed up. Look at me. Look at me. Oh, it's just and I don't have time to make you a new video either, so I'm not even going to pretend like I'm perfect. Anyhow, I added the VI to both sides, so I have VF is equal to the VI I added over here. I'll just write it in. So the VI that I added on both sides, and then I moved this whole chunk over here and this chunk over there. This is going to be the first of our kinematic equations. So the final velocity is going to be equal to the initial velocity plus the acceleration times the time. By the way, in all of the kinematic equations that I'm going to derive for you today, we are going to assume that acceleration is constant. So I'm going to write that up here. Assuming acceleration is constant. And I'm going to put an exclamation point. So these equations assume that acceleration is constant. If you don't have constant acceleration, none of these equations are going to apply. All right, so here's the first one. The final velocity is equal to the initial velocity plus the acceleration times the change in time. All right, for my next magic trick, let's talk about average velocity. So your average velocity is defined two ways. Those two ways are, they can be defined as the change in the distance over the change in the time. But the average can also be defined as VF plus VI over 2. So I add up my two velocities and divide them by 2. If we set these equal to each other, let's go ahead and do that. We will get the change in x over the change in time is equal to VI plus VF over 2. Now let's say I solved for the change in x. Well, that's pretty easy. I'm going to multiply both sides by delta t, and I'll get the change in x is equal to VI plus VF over 2 times the change in time. Now, I can write this this is a little awkward, so I could write it this way. I could take that over 2 and make it a 1/2 out front. I am not being consistent with what order I put VI and VF in because it doesn't matter. I'm adding them. It doesn't matter what order I put them in the slightest. And a foolish consistency is the hobgoblin of small minds, as Ralph Waldo Emerson said. So, here we go. This is our second kinematic equation. So the change in the distance is equal to 1/2 of the final velocity plus the initial velocity multiplied by time, the change in time. All right, let's try something a little different. I'm just going to play around with this. What if let me move this paper up so you can see. We solve the definition of acceleration for the change in time instead of solving it for VF. So we started this whole journey with this equation here. What if we instead solved for delta t? So that's real easy. You multiply both sides by delta t, you get a delta t is equal to delta v. And then you divide both sides by a, and you'll get delta t is delta v over a. And delta v is vf minus vi, so delta t is equal to vf minus vi over a. Well, why would I do that? That seems like a pain in the backside. But here's something really cool. Well, I think it's cool. You may not think it's cool, but I think it's cool. If you were to take this thing here, which is just the definition for acceleration rearranged, you solve it for the change in time. If you were to plug it back into this kinematic equation up here, you could eliminate time altogether. Holy mackerel, let's do it and see what happens. I have a feeling that something mathematical will occur. So the change in x is going to be equal to 1/2. I'm going to put brackets here, otherwise I'll get parentheses inside of other things. So let's say that you had, no, I won't, but it'll make it easier anyhow. VF plus VI times, now this stuff here, VF minus VI over A. Okay, let's see what we can do. Boy, that looks annoying. Well, let's move the 2 to the other side because that's an easy step. That'll make my life better. Oh, and look, this thing is over A. So I could actually multiply both sides by 2 would get rid of the half, and A would get rid of the A. So if I multiply both sides by 2A, then the 2 and the half would become 1, because if I multiply 2 by half, that's 1. And A times 1 over A becomes 1 also. That's cool. All right, so this kills, and this kills, and I'm going to get 2A delta x is equal to VF plus VI times VF minus VI. Oh, you should recognize this kind of thing. Y'all have done the sum of squares, the difference of squares, that kind of thing before. So I bet you know what's coming, or I hope you do, if you've had a math class before. So this times this is going to give us VF squared, and this times this is going to give us negative VI VF, and then this times this is going to give us plus VI VF, and this times this is going to give us negative VI squared. And so since I have, these are opposites of each other, VI VF and negative VI VF, those kill each other, they annihilate, that goes to 0. And I'm going to get VF squared minus VI squared is equal to 2A delta X. And I'm going to just rearrange it because the way I memorized it since I was a teenager, this comes first. So I'm going to rewrite it that way just because it's easier for me and I'm older. And so my knees are the ones that hurt, yours don't. So I am just going to do what's easiest for me. Isn't that cruel and unusual? Okay, so this is your third kinematic equation. I want to point out what's really cool about this. This equation doesn't have time in it. Time is nowhere in it. So if you are given a situation and you don't know how long an object is moving, but you know some other important things, you can solve all kinds of stuff using this equation, but you don't need time. This is an equation without time. That's nifty. In fact, let's go back over to some of the other stuff we've looked at. Look at this one. What is missing out of here? So this is an equation without acceleration. There's no acceleration in this equation. Ain't that nice? Yeah? And look at this equation. This is an equation without distance. I don't know how far I went. See, there are 5 kinematic equations, 5 kinematic variables. You have the final velocity, the initial velocity, the acceleration, the time, and you have the distance traveled. And if you're just missing one and you have the other 4, you can solve any of these equations. And that's what's awesome. So, yippee. That's equation 1, 2, 3. What do we have left to do? Okay, I guess also, it's the one we did yesterday. My favorite equation, delta x is equal to 1 FAT squared plus v initial times time. So here's how we can get there with algebra. Also, we can plug PLUG, oh my goodness, I can't spell, number 1 into number 2 to eliminate the final velocity. So let's do it. Let me just double check what number 1 and number 2 were. I wrote this down earlier this evening. What was number 1? Number 1 was VF is equal to VI plus A delta T. And number 2 is delta X is equal to 1/2 times VF plus VI delta T. Yeah, I can do that. If you take this sucker here and you plug it in for this value of VF, that's what we're going to do. That seems reasonable. We can eliminate VF. So what I've got is number 2 modified. Delta X is equal to 1/2. Now this time I do need brackets. So VF is the same as VI plus A delta T. So I'm going to put in VI plus A delta T plus VI times delta t. Let's make sure that we have everything. We've got our 1/2 here. We've got VF inside these parentheses, and VF is VI plus A delta t. All right, so that's VF plus VI. That's inside these brackets. Yep, and all of that is multiplied by delta t. Now we can get rid of some extraneous stuff that we don't need. Like, you see these artificial parentheses in here? We don't need that because it's just addition. So this is going to be equal to 1/2 times VI plus A delta t plus VI. Okay, I have two VI's in there. 2 VI plus A delta t. Oh, I'm starting to see this coming together. I'm very pleased, very, very pleased. So that means if I distribute my 1/2 inside, then I'm going to get 1/2 of 2 is 1, so VI plus 1/2 A delta t. And I multiply everything by delta t. So if I distribute my delta t in, oh, that is just beautiful. Oh my goodness. So that is V initial delta t plus 1/2 A delta t squared. That's the change in distance. Oh, folks, that's enough to make a strong man weak in the knees. That is beautiful. That is absolutely stunning. Look at that. That's what we came up with yesterday. Holy mackerel. We got the same answer with algebra that we got with our graph. Look at that. All that work with our graph, it's the same thing. Isn't that marvelous? That is just spectacularly beautiful. Holy mackerel. Isn't the world just an astonishingly marvelous place? All right, let me give you something that you can practice on. I don't know how long this video has been going, but I assume that you will have some extra time in class, so let me give you something to keep you occupied. In your book on page, this will be your homework. I will check it tomorrow. On page 59, numbers, there's a bunch of easy stuff. I don't want to give you something that's too easy. You'd be bored. Well, I guess I don't have much choice. I'll give you a couple easy things, and we'll see how you do. How about that? Let's give you number 27 through through 31. That might be too hard for you. That might be too much. But I want you to do 31. No, I want you to do them all. I really do. So that's your homework assignment. You have the rest of this class period to do it. And if you're not finished in class, do it at home. I hope you have a marvelous day. And I look forward to seeing your bright faces tomorrow. Take care.